Let's solve Laplace's equation in a really inefficient way. Suppose we have a trapezoid-shaped metal heat pipe, and the bottom side is in contact with the heat source, while the top side is in contact with the heat sink. And for mathematical simplicity, let's assume that the heat source is controlled to run at exactly 100 degrees, which is a typical hard limit for CPUs. And the top side is connected to an ice water reservoir, with the water pump running sufficiently fast to keep the water in contact with the metal fixed at 0 degrees. And let's also assume that the sidewalls are completely insulated, so heat flows only from bottom to the top. Let's assume that metal is initially in thermal equilibrium at room temperature. Then you turn on both the CPU and the water pump simultaneously. Then the temperature of the metal will change until it reaches a steady state temperature gradient. And this eventual steady state satisfies Laplace's equation. This is the heat equation, which describes how temperature changes over time due to heat flow. And this is the Laplace's equation. So we can just solve the heat equation and wait for the temperature to eventually settle to a steady state.